Here's a preview of Nengi's latest client-side prediction API and deeper integration with a 3D renderer. This game is made with Nengi and babylon.js. Now, 3D things have been integrated with Nengi before, but they're used purely as a renderer. What's special about this game is that Babylon is, for the first time, running on the server side. Babylon has in it something called null engine, which is an instance of its own engine that doesn't do rendering and only has the rest of the logic. Babylon has not just rendering in it, it has collisions, it has integration with physics, and it has a whole bunch of handy three-dimensional math. So this game runs null engine on the server, and it runs regular, normal Babylon with its renderer on the client, and this allows us to make a simulation and run essentially the same code on both the client and the server. This game does exactly that. The items of interest are the terrain mesh and these two walls, which I'll be colliding with to show some of the client-side prediction and recovery features. I'm playing as the cube. Well, I'm controlling the screen on the right, and the screen on the left is just another player sitting there who's looking at me. I'm going to aim this other player at this wall, so we have two perspectives on these collisions I'm about to perform. And then I'm going to grab this other player and crash into the stuff. So this mesh is procedurally generated using kind of organic noise algorithms that we see commonly used in everything. If I fly up into the sky here, you can see the kind of just organic shapes it has. I mean, I haven't put any textures or trees or anything in here, but it's essentially a simplex noise or a Perlin noise-esque landscape. This landscape is generated with a seed, meaning deterministically you pass it a seed and the same landscape comes out every time. And the client and the server both generated the same landscape from the same seed. So there wasn't any need at any point to actually send the map data from client to server or server to client or anything. They never exchanged anything except for the seed, which means it took no bandwidth, essentially, to load this map. With them both having the map, they can both run identical collision logic between the player and the mesh, which produces this behavior that allows me to slide along the mesh and run around and conform to it perfectly. And it's predicted, meaning that I don't have to wait for the server to say, oh, here's the result of your movement. The client can tell what's going to happen. The same is the case for this gray wall. This gray wall exists both on the server and the client, and collisions with it can be predicted very well. As you can see, the actual collision involves my cube hovering a little bit. My cube hovers about half a cube above the things it hits. I can also crash into the wall, and I get this nice smooth collision. I can slide along it, and this is also predicted. The pink wall exists to demonstrate what would occur if there was an error in the prediction. The pink wall is being simulated on the server. Well, simulated. It exists on the server, but it doesn't exist on the client. For the sake of us having something to look at, I've drawn this pink shape where the wall is on the server, but the client itself believes that there's nothing there and that I can travel right through it. So if I collide with it, the client's going to predict that I continued moving up until it gets a data comes back from the server saying, oh, you weren't allowed to move. So if you look at the right screen, the screen that's being played on, we can see that as I move into pink wall, I get some sort of error, and I rubber band horribly. This is how far we made it at whatever latency we have into the wall before we got some sort of message from the server saying that our prediction was wrong. If you look on the left screen, the one that's just the onlooker, you'll see that nothing bad ever happened. It looks, the collision against the pink wall and the collision against the gray wall look like the same kind of collision. It's just a perfectly smooth hit. The reason for that is that that's the other player, and that player isn't predicting anything at all. It's just displaying the world that was sent to it by the server. And that world is a world in which this cube never thinks it can make it through the pink wall. Now, to show this API and how simple it's really gotten over a few iterations of Nengi, let's take a quick look at the code. The actual code for moving a player and registering a prediction about where it's landed comes down to 1 or 2 lines. We run our movement logic. That can be anything. Here it's just called entity move. And then we register a prediction. We say this client add prediction, and we pass to it the tick from the client, whatever step we're on, the entity we're predicting, and the properties which we'd like to know about if there's an error. In this case, this game says it's predicting X, Y, and Z, and that's all there is to it. The server will run our movement logic after it receives our commands, same as us, and at some point in the near future, after our command is received by the server, we'll get data back on the client, which will show our new position. And when we get that, Nengi will automatically, after we've registered this prediction, check to see if the X, the Y, and the Z, or whatever we told it we're predicting, came out to be the same thing that we had predicted. If they are the same, nothing needs to happen. We continue moving. Everything's great. If instead, though, as is the case with this pink wall, the server says to us something else, it says some X, Y, and Z other than what we'd predicted, we enter the stage of needing to reconcile the prediction or correct this error. The error code, which is something I'll cover in a more specific tutorial, can be seen here and is a couple dozen lines, and which is much easier than these things have been in past iterations, but it basically consists of snapping our player back to the position that they were at when we made the mistake, correcting the mistake, and then for as many commands as we sent to the server since the mistake was made, we run them over again and catch ourselves back up. Now, that's a very whirlwind explanation, or not even a real explanation of client-side prediction, and I will be writing some tutorials that get at it in depth, but I just wanted to show here how little is actually needed to get full predictions working nowadays, as opposed to before when it was quite an elaborate process. Really down to a line or two to do the collision or do the prediction and register it, and then a dozen or so to reconcile any potential error that comes from it. Now, going back to the demo itself, I'd like to show how well the predictions are working and how much they truly are concealing. One way to do that is to load up this nifty little program and tamper with the network data. What I'm going to do is I'm going to throttle my outbound packets by 150 milliseconds, so I'm adding to my latency, and then I'm going to drop 10% of the packets. Now, this is an absurdly unrealistic amount of packet loss, but it will work for this demonstration I'm going to do because it'll be very evident. This much packet loss is truly horrible. Like, you usually can't play a game with this much packet loss at all. Bad packet loss is already around 1 or 2%. By the time you're at 4%, things are horrible. This is 10%. I mean, some things would just disconnect you at this rate of packet loss. In any case, let me get the 2 players open again. And I've only throttled the outbound packets, which means one player is going to be able to see the game as it is. Well, basically meaning we're only going to have lag in one of these, because one's watching and one's sending input. So we're going to get to really see the lag. So let me get them so they can see each other. And I'm playing on the right screen, and the left screen is looking at me. And I'm going to jump up in the air. And you'll see on the right screen, I'm moving up and down smoothly, but on the left screen, I'm sliding up and down in very big, discrete chunks. And if I start to move around a lot, you can see that in the perception of the other player, I'm lagging horribly. But in my own perception, once again, I'm playing on the right screen, everything looks fine. It's as if I'm playing a single-player game. I don't even feel that I have 10% packet loss and 150 latency added on top of whatever the latency is between West Coast and East Coast. We will see some manifestation of this, though, in the player experiencing the lag, or some manifestation in their own experience. For example, if I go and collide with this pink wall again, we'll see that the collision with it, or the reconciliation of it, has gotten even more dramatic. In fact, as I jump through it, I perceive myself as almost as if I firmly passed it. In fact, I can. I make it very deep past the wall. Well, it depends on packet loss. Packet loss is a random process, or at least it is through this program. So it's really, the roll of the dice to see how many packets get dropped. But you see, with bad packet loss, there is a pretty big rubber band distance for me. Now, the parts that are impressive about that are that even with my connection degraded that badly, except for when there is a actual predictive error, which, there's none against the gray wall, none against the terrain, and the pink wall is, contrived for the sake of creating the error, I can still play this game at, 144 frames per second and horrible connection metrics. Now, a note about this lag that the other player sees. If we were to actually leave something like this in the game, make it so the game is playable by somebody who has 10% packet loss, as it is now, and let them run around the game, with nothing else going on, and the game were to be a shooter, some sort of competitive game, that would be pretty bad because players with packet loss would be very difficult to hit. And it's not the case that that has to be that way. It's just the case that for this demonstration, I'm letting the raw network data through. The trick to making even this part go away is that when somebody's connection is that bad, you can have two player positions for them. You can have one which they perceive themselves at, which you keep track of on the server, but the actual player position that you show to all the other players who are watching will be a smoothed player position. And that's also the player position you can use for collisions when the other players are shooting at them. And then the player goes back to moving perfectly smoothly, even though they're experiencing horrible lag. Their lag will still manifest in some ways, you just won't see it visually. Their lag will manifest in, well, if they shoot at something and we're waiting to see its hit points drop, we'll feel their latency. If they were, picking up items off the ground in the game, they would once again feel the latency. It just depends on what exactly we've applied prediction to and what we haven't. We haven't magically solved lag. We've just sort of smoothed it all over. In any case, a more detailed, an actual, tutorial for the new prediction API will be appearing on the website after this is all done, and as will a template game showing Babylon.js integration. Thanks for watching.